Welcome back to ECE 442-542. We're in lecture 6.3, which is dealing with PI controllers and using examples to help illustrate what we will be able to do with PI controllers. PI stands for proportional and integral. We now have these two different parts to our controller, a proportional part and an integral part, that we're combining in a PI controller. In this unit, we are going, or in this particular segment of lecture 6.3b, we will introduce the PI controller, and the way that we will do that is we will refresh our memory on the proportional controller, block diagram, and how it's structured. Then we will introduce the PI controller, or actually derive where this PI controller is coming from. We'll mention a couple of properties of the PI controller, and then we will start with the PI controller in a block diagram and show how we can convert to the standard root locus form, which is really illustrated here in the proportional control, where we isolate out the proportionality gain k from the rest of the poles and zeros. Here we're calling that our plant. With a proportional controller, we do just have a constant gain k controller. The idea is, can you pick a gain k? Let's say k is equal to 4 or k is equal to 57. Can we find a k that would give us the properties that we want to accomplish, mainly stability, possibly some transient performance characteristics, settling time, percent overshoot, peak time, and maybe steady state accuracy. With this particular structure, this is now our standard root locus form. We can derive this, should be able, you could do this in your sleep now. This is kg over 1 plus kg. In general, it's cg over 1 plus cg. Here, c is just a proportional controller, k, meaning we now have our closed loop transfer function, capital T sub c of z, being equal to kg over 1 plus kg. And the denominator of that closed loop transfer function does govern the dynamic behavior of our system. So 1 plus kg of z, and we can now find the values of z that cause that to disappear. That's now our characteristic equation, 1 plus kg of z equal to 0. For a fixed gain k, that will then produce certain z's that satisfy that. If you now had a fifth order characteristic equation expression, you might have a fixed k. K is, let's say, 7. Now you have 5 values of z that satisfy that particular expression or equation for a fifth order. And those 5 z's will now, if you wanted your system to be stable, all 5 of those would have to be inside the unit circle. If you had 2 of those that were dominant, closer to the unit circle in terms of their radial distance from the origin, those you might then try to adjust or have placed in a particular location in the unit circle to satisfy performance specifications. That's the proportional controller, where the k is the adjustable parameter. G consists of our poles and zeros of our original system or the original plant, and we are now controlling that in a closed loop setting. What about a PI controller? This is now combining a proportional action and an integral action, and you can see that now in the analog expression. U of t, the input to the plant, is a constant multiplication of a gain, k sub p, times the error signal, plus another gain, k sub I, times the integral of the error signal. And this k sub p and k sub I are adjustable knobs. We can now independently move k sub p between 0 and infinity, and we can also adjust k sub I independent of k sub p between 0 and infinity. Now we have two knobs to adjust in a PI controller, and you would expect you now have a little bit more ways of manipulating the behavior of your closed loop system. If we now take that time domain relationship for the PI controller, this is a proportional gain on the error and an integral gain on the integral of the error. Now we can take that into the frequency domain by transforming that equation, and we have capital U of S on the left is equal to k sub p times capital E of S, or the Laplace transform of the error signal, plus, and now what does an integral look like when you take it into the frequency domain? That's now division by S. So now you have k sub I over S times E of S. That's now what the PI controller looks like relative to the error, and that error signal is usually a comparison of the reference input with the output. That's how we build or generate this error signal. We scale it, and that's the proportional term in our PI controller. We integrate that error and scale that with k sub I, and that's the integral term. Let's now see what that PI controller looks like in a discrete time setting. And we can find that. One way to do that is to say, we just finished up a unit 4 on discrete equivalence. Let's now go back to that and say, if that's the case, and in particular you might look at the fourth installment in that unit. Lecture 4.4 was dealing with numerical integration strategies, and we had three different ways that we looked at. One was the forward rule, one was the backward rule, and one was the trapezoidal rule. Just for convenience, let's just go ahead and say, let's now transform this relationship in the analog domain into a discrete setting by using the forward rule of discrete equivalence. So now we're going to substitute everywhere we see an S in these operation locations. We're not worrying about the argument on E of S. This is now replace S where it's as an operator in this expression for U of S. And the only place that occurs is in the denominator of that integral term. We now can say, oh, U of Z, the Z transform of our input signal, is now k sub p E of Z plus k sub I, and now we do the substitution. We replace S with Z minus 1 over capital T, and that's now what our PI controller looks like in a discrete time setting. We can now clean that up a little. Let's factor out the E, and let's multiply that coefficient or scaling factor that's scaling the error on the right. Let's multiply that by 1, which is T over T, so that we now have k sub I T over Z minus 1. So we're just factoring out those two terms that are now collectively scaling the error signal's Z transform, capital E of Z. We can do a little bit more algebra. Suppose we put everything over a common denominator. That means we need to multiply the numerator in this form, k sub p times z minus 1, so that those z minus 1s would cancel, and we're left with what we started with, which was a k sub p plus, and now we haven't changed anything. That's still over the same denominator of z minus 1. Remember, capital T is our sample period. Z minus 1, now you can see that in fact we do have a pole in this controller. This is really our controller's transfer function between the air signal E and the output of that controller, which is U. So this bracketed expression is really an expression for our controller's transfer function, and that possesses a pole at z equal to 1. Let's distribute that k sub p. We can now combine the constant coefficients. We now have k sub p times z, and let's just subtract from that. So now we have k sub p z minus k sub p and a minus k sub I t. We're really just performing some algebra, manipulating this expression so that it all starts to look a little cleaner in terms of what that's producing. We can now factor a k sub p out of both terms in the numerator expression so that we now have a gain scaling some factor. And that factor is representing our 0, and in this particular case, we can say, oh, that particular constant, suppose we now said that constant is an alpha, which it is. It's just some combination of the proportional gain k sub p, the integral gain k sub I, and the sample period t. Those are all numbers once we've adjusted those knobs k sub p and k sub I. Now we have our transfer function between our air signal E and our input to the plant U. What's in between that is the transfer function of our PI controller. If we now replace that expression that I've highlighted in yellow with just an alpha, this is now our generic structure for a PI controller. You see that we have a pole that's fixed. Once we said we had a PI controller, we now have a fixed pole at z equal to 1. That gives us now this integral action. We also have, by the choice of these two adjustable knobs, k sub p and k sub I, those we've now actually hidden behind this alpha, but if I now pick an alpha, I can back out k sub p and k sub I because I know what the sampling period capital T is. The PI controller then says, oh, if somebody says, I want to design a PI controller, you immediately know that you have some gain, a 0 factor, and a pole at z equal to 1. So we have a fixed pole at the denominator, or in the denominator, and that fixed pole is at z equal to 1. We have a 0 factor, and we can now manipulate that 0 location in the complex z-plane, and we can also adjust the gain k sub p. Now when somebody says you have a PI controller, you could think of this structure is what you're working with. What are some of the properties of a PI controller? First, you can see that that denominator is fixed. Once you say PI, I gives you integral, you now have a z minus 1 factor in the denominator. That forces an open loop pole in your controller, in your PI control, at 1, at z equal to 1. So what? Well, a pole at 1 allows you to improve your steady state accuracy. So, even with that pole there on the unit circle, if you can now have your closed loop system being stable, then this will, having that pole at z equal to 1, improves your steady state accuracy, or it allows you to actually track constant inputs. Meaning, if you can stabilize the closed loop system and you have a PI controller, now if somebody injects a 3 into your system for the reference signal, your output is going to track that 3 after the transients have disappeared. So now, after your settling time, and you can determine what that is based on your closed loop poles, but now after that settling time, you will go towards that, or you will be at that constant reference input, whether that input is 3.1414, whatever, or if it's 7, your output is going to track. That's a good property. You now have the ability to enhance your steady state accuracy. The PI controller provides you with an adjustable zero location. You can change that alpha wherever you want, and that really just corresponds to allowing you to adjust the proportional knob and the integral knob in this PI controller, because you can actually buy a PI controller and it will effectively have knobs. Actually, you'll buy a PID controller, you would just set the derivative knob to 0. Now you adjust the proportional knob and the integral knob on that PID controller, and that adjustment is effectively allowing you to manipulate the 0 location in that transfer function of your PI controller. And you can adjust the gain. What that's saying then is the PI controller has 2 adjustable parameters. The proportional controller has the 1 adjustable gain parameter. So as we increase the number of letters in our PID controller, you would expect to have more and more flexibility in the design of your controller. P, you have 1 adjustable parameter, the proportional gain. PI, you now have a proportional gain and you have an integral gain. You have 2 adjustable parameters. Well, do we have to completely rethink how we design our system? Not really. Let's look at the block diagrams. Here is our plant, G of S, some plant, some system that you're trying to control, controlled with a PI controller. So this is now a PI controller. PI controller, we have a fixed pole at z equal to 1. That's the z minus 1 factor. We have the ability to adjust the 0 location by manipulating alpha, and we have the ability to adjust the gain k in that system. Well, we can actually convert that, or make this block diagram look like the standard root locus structure if we take this term and move it in here, and we take this term and move it in there. Now we can essentially isolate the adjustable gain k. We obviously will need to select an alpha, but once we select a 0 location, now we have a G bar of Z being controlled with a K bar. And this we can find. Here is the PI controller. There is our original plant G. We have CG over 1 plus CG. But in this restructured block diagram, we've now pushed the pole at 1 and the 0 at alpha into our generalized plant block. And now what we still have available to us is the opportunity to adjust a single gain K bar once we've fixed the 0. And again, we can manipulate the dynamics of our closed loop system by adjusting that K bar, and we now are going to learn how to manipulate that K bar by using rules known as the root locus design rules. So once we now have this structure, we can use our root locus strategy to figure out or determine how do our closed loop poles that are determined by this characteristic equation, how do they move through the complex plane in response to changing this gain parameter k bar from 0 to infinity. That's those red branches that are on our z-plane. We now want to adjust k bar to create those red branches and then see if there are values of k bar that would produce simultaneously locations on those branches that would give us our desired behavior in the closed loop system.